The classification algorithm is a supervised learning technique that is used to identify the category of new observation on the basis of training data. In classification, a program learns from the given data set or observations and then classifies new observation into a number of classes or group. In this video, you will learn about comparison between some of the most common and popular classification algorithms and see the factors that lead to comparison. You will also see how to evaluate each and every algorithm's performance based on a case study and finally summarize everything. So if you feel the need to dig deeper into real-time application of classification algorithms, sit tight as we bring to you all the information that you need right on your screens. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoy this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions and I will respond to your comments.
Welcome everyone to today's session, and what we are going to today do is we are going to compare some of the common classification algorithms out there. Now, along your different courses that you have gone through at Great Learning so far, you would have encountered several classification algorithms, and what we would try to do is we would try to attempt to understand when is it more suitable to use one algorithm versus other algorithms which we have out there. Now, what we are going to do today is we are going to compare some common algorithms that you would be familiar with. We would be starting with the logistic regression, and then we will go with the support vector, followed by k-nearest neighbor, naive Bayes, decision tree, and random forest. Now, before we decide that how do we compare these algorithms, the first thing that we would need to do is understand how is it that we are going to compare these different algorithms. What would be some of the key factors that we are going to use to compare these different algorithms? And what we are not going to do is spend too much time discussing how these algorithms work. So we would be doing a very small intro on these algorithms because we would be assuming that you have already gone through these algorithms through your different courses. We will discuss them briefly, but we would not be going into the details of how these algorithms work. Finally, after we have a brief intro about the algorithms, we would be comparing their performance on a common data set. And the case study that we are going to work on is a case study on promotions. We are going to use these algorithms to try to predict which candidates, which professionals working in a company are more likely to get promoted compared to others. And finally, at the end, we are going to summarize our findings on where do we feel that these algorithms fit better. So the 4 parameters we are going to use to compare these different algorithms are model performance, time, hyperparameter tuning, and decision boundary. So let's talk about each one of them a little bit. When we are talking about model performance, what we mean to say is what is the accuracy, or what is the mean squared error, or what is the root mean squared error. So depending on what kind of tasks which are there are different kind of metrics. When we talk about classification problems, the popular metrics are accuracy, and there's also F1 score. And can you tell me some other metrics which are popular for classification? So maybe you can join in and type it on the questions panel. Any other metrics that you are aware of which are used to evaluate? Recall is a popular metric. Precision is a popular metric. And in fact, F1 score, another popular metric, is just a harmonic mean of recall and precision values, sensitivity. So yes, all these are important ones. There's one other metric which is very famous, AUC, area under the curve, and receiver operator characteristic, ROC, is also an important metric. So yes, these are all important metrics to evaluate classification algorithms. So in the first part, we'll actually look at these values to evaluate which of the model shall we use. And we'll be choosing one of the metrics over here based on our data set, and then we would compare the different algorithms on some of these metrics. The second part is how much time does it take to run a particular algorithm? And another way to mention time is computational efficiency. How long is it going to train that particular model? Now, even though nowadays we are living in the age where computation is not that big a challenge, but still, if we have a very large amount of data set, then tuning a model using with hyper tuning and making our model perfect can take a lot of time, can take a significant amount of time. Not all of us have access to, let's say, GPUs or maybe expensive resources like AWS and so on. Now, AWS is no longer that expensive, but still, uh, there's a cost for time as well, right? So time spent on running a particular algorithm, and we could have done something else at that very same time. So there's a time component to these algorithms as well. Now, there are different hyperparameters which are also associated with these algorithms. Depth is one of the hyperparameter, or max depth, I believe. So hidden layers, that's for neural networks, but anyways, let me just mention it here. Number of trees, learning rate, okay, fair enough. How about some hyperparameters for logistic regression? Okay, so one is solvers, kernel. Kernel is a hyperparameter for SVM, and a very important one, C. In fact, C is a hyperparameter which is there for both SVM and logistic regression. All right, fair enough. So what we are going to try to do when we talk about hyperparameter tuning is how many parameters do we need to tune, and what is it that these parameters work with, and how is it that these parameters affect our model when we try to tune them. So we are also going to understand, is it difficult to tune a hyperparameter for a particular algorithm, or is it easy to tune those algorithms? So these are the kind of things we are going to discuss. And finally, this is maybe something that you have not seen it so far. We are going to understand how is it that decisions are being made by a particular model. What is the kind of decision boundary is the model that the model is making? If the decision boundary is quite complex, we can say that the model is quite complex. And complexity of the model is not always desired. If it improves our performance, yes, complexity could be good, but otherwise, complexity can also be associated with overfitting. Generally, if we talk about more complex models, they can be highly prone to overfitting. So this is something that we are also going to be wary of. We are going to understand how is it that our different algorithms are deciding. And since we are talking about a classification algorithm, and particularly we are going to talk about a binary classification problem where we are going to have two classes, we are going to understand how is it that the model is deciding that one sample should belong to, let's say, class 0, and the other sample should belong to class 1. So these are the different parameters that we are going to evaluate today. And at the end of our session, we will like to fill this kind of table where we would have all the popular classification algorithms out there. So you'll be covering the basic classification algorithms that you might have covered: logistic regression, SVM, KNN, naive-Bayes decision tree, and random forest. And at the end, we like to sort of write down our results on model performance, time taken, hyperparameter tuning, and model complexity is something that we are going to denote by how likely is the model to overfit. So again, XGB, I think somebody is mentioning XGB. We are not going to discuss, we are not going to use XGB. That said, at the end, if we have some time, I can give you some intuition about XGB. So that is something that we can take on later on. We have seen what is it that we want to fill into our table. Let's look at the problem that we are facing as well. This is the case study we are going to go through. So there's a company which has contacted us, and this is a large company with a lot of employees all across the globe. Now, what this company does is, this company at regular intervals conducts trainings for the employees. Now, based on the performance of the employees on these trainings, as well as other factors like how well they have done their projects, what is the relationship with the management, how is that the person dealing with it with their peers. So based on other complex factors, the company decides whether to promote a particular person or not. Although training score tends to be one of the key criteria on deciding if a particular candidate needs to be promoted or not. But the process of conducting the training and then evaluating the results, getting the performance, sharing it with the management, that process takes a lot of time for this company. Now, when we talk about a lot of time being taken, it also means that these employees who can potentially be promoted are not taking on their new roles, which is a potential loss to the company. Because let's say there's a 3 to 6 months delay in the people joining their next desired roles. And that means they're not able to take additional responsibilities till they get promoted. And that's a little bit of a loss for the company. So the company has contacted us and they have collected some data regarding the performance of these different people or different employees. And they want us to generate a machine learning model, to develop a machine learning model through which we can probably predict in as accurate manner as possible on which employees can get promoted. Now, our objective for this case study is not to actually maximize the performance of our model. Our objective is just to understand which of these algorithms could be better for this case study, right? So we are not really going to try to get the maximum juice out of the performance metric that we are going to evaluate, but rather we are going to focus on the approach that we have taken in terms of the algorithms and how is it that these algorithms are learning from the data in hand. So if we talk about the data set, we have these 14, 13, 14 columns into our data set. So we have the unique ID of the employees, and we also have the department, which department do they belong to, sales, marketing, operations, technology, and so on. We also have which region are the employees working in, and it is coded. So we don't have the actual names of the region, but it is coded in terms of region 1, 2, 3, 4, and so on. There are several regions out there. When we talk about education, there are few fields. There's masters, there's bachelors, and there are a couple of few fields, couple of other fields as well. And in fact, there would be some missing values as well. We have the gender component. We also have how is it that the people were hired? Were they referred by someone, or was it through a sourcing sort of platform like maybe Naukri.com or any other platform, or maybe it was some other platforms like maybe a message on LinkedIn and things like that. So maybe that also has an impact. When we talk about, let's say, if people are referred, then maybe they are sort of preferred by the management. So there could be biases over there. Everybody working in a company, it essentially has all the biases that we as humans have. So there could be some biases based on the recruitment channels as well. We also have the number of trainings that people have been conducting. So the number of trainings that employees have gone through at the company. What do you think? Is it going to have a positive impact or a negative impact? The number of trainings that people have gone through. Finally, we have age. Age again could have a mixed impact in terms of things because maybe at a very higher age, people would not like to promote people who are very, very senior. So that could happen, right? Similarly, at the other end of the spectrum as well, if people are too young, again, people might be a little wary of promoting them. So again, there could be a mixed impact with age as well. Then we have something which will capture loyalty. How long have the employees been working for this particular company, right? So again, loyalty could be again twofold. Mostly should be positive, but there could be some surprises with loyalty as well. Finally, we have, let's say, at each, maybe at the beginning of the annual year, each employee is given certain targets to fulfill during the year, and they are being referred to as key performance indicators. And we have a Boolean over here, we have a true, false, or 0, 1 kind of value, whether the employees have met those key performance indicators, or maybe have they met 80% of the key performance indicators or not. Similarly, have they won any award? Have they won any award during their tenure or not? And we don't have the training score for the current period because the objective of this exercise is that maybe we can predict who is getting promoted without conducting a training. But we do have the average score of all the trainings conducted in the past. So how much have they scored in the past? We do have the average score over there. And finally, we have our target variable, which is promoted, which is a 0 or 1. 1 means promoted, 0 means not promoted. All right, so these are all the features. So it appears that apart from employment ID, all the other features could be important. So we are not going to drop any other features. We are going to retain all the features. Now, for this particular session, we are not going to actually evaluate on which of these features are actually important or not. It is just for our discussion that while we are looking for a case study, initially, should we look to remove certain features or not? Our focus would be only towards evaluating the algorithms. We would not be actually evaluating on which feature has an impact in this data set or not. That's it, but it would be a fun exercise for you later on, since you would get the access to the notebook as well as the data set. So what we are going to do now is we are going to go ahead and to our Jupyter notebook, and we are going to process the data, make sure it's ready for machine learning, and then we will start comparing the algorithm. So we are going to do a little bit of pre-processing of data, make sure everything is ready for the algorithm to run. Let me jump over to the Jupyter notebook. All right, so first of all, we are going to import the three standard libraries for data science: NumPy, Pandas, Matplotlib. And I'm also going to make a few custom settings for plotting. And it is optional. You can change these settings later on if you want to. And this is particularly a function that we are going to use to understand the decision boundary of it. Now, this is a long function, so I'm not going to explain it in detail, but we are going to get the gist of it on what is it that we are trying to do. What we are trying to do in this function is we are going to have some input data and some target variables, and we are going to use different classification algorithms to create a model for us based on particular data set. Now, while we are using this function, we are only going to use two features. So we are going to use two features. The reason being is that eventually we want to make a plot. And we know whenever we plot something, we have a little bit of handicap that we can only plot something which is of 2 or 3 dimensions or one dimensional, not more than 3 dimensions. And again, when we talk about 3 dimensional diagrams, they can be sometimes a little bit difficult to interpret. So we are only going to train on two features with this particular function. And what this function would do is this function will give us an idea that what different combination of values of these two features will be predicted as class 0 and class 1. So this is what this function will do. We will talk about it in more detail once we actually run it on a particular algorithm. So let me just run this function. And now what we are going to do is we are going to load the data set and explore it briefly. We are not going to explore it too much because our agenda today is something slightly different. So once we look at the data set, we see that we have around 43,000 rows and 14 columns to work with. If you look at the top 5 rows, we see these are the columns that we were discussing about. We have the employee ID, department, region, education, and we have our gender, recruitment channel, and so on and so forth. So maybe looking at the data set, can you tell me, is it ready to be used for machine learning, or do we need to do some pre-processing? What do you think? We have the awards one, KPIs, and so on. And finally, we have our target variable over here. All right, so one tool that I like to use to quickly analyze the data is frame summary, and that is from a library called Pandas Summary. So if you don't have it, you can easily install it using Conda or pip. And this helps in analyzing the data quite nicely in terms of particularly the missing values. So how it works is that after we have imported data frame summary, we pass it on to our data frame. And after that, if we look at the column wise stats, and what we are doing after this is we are transposing these values. It very nicely tells us which of the columns contain categorical values, and particularly it talks about text columns, all the columns which are text values like recruitment channel, like education, region, and department. So it tells us that these are categorical types. Very nicely for us, it also gives us how many values are missing, what percentage of values are missing in a particular column. So we get to know that education, which has text values, also has missing values. Previous year rating, although numeric, is also having some missing values. We also get to know how many unique items are there. So we see there are 34 regions. If we use one hot encoding to convert regions, then we are going to get 34 columns. So that's can be a little bit too much. Maybe that will increase the computational cost. So as of now, we are going to not do that. And finally, we have a target variable, which is having two unique values. That's a Boolean. And there are a few other Booleans as well. Awards one, whether the KPIs are met more than 80% and or not, gender, and so on. So we have quite a few Booleans in our data set as well. And we have some numeric data sets as well. So first thing first, we do need to clear for missing values. We see that our previous year rating and our education column has missing values. Let me just correct it over here, education and all right. So these two columns have missing values. So what we are going to do is for education, because it contains textual data set, we are going to use no record. So to correct for the education column, what we are doing is we are filling it with text. You can use any text. I'm just using a text of no record, and we are using the fill na function over here. All right, so we fill in the education column, and what we are doing for our numerical column, which is previous year rating, is we are filling that with median. Some of you may argue that why not mean, and I would say that fair enough. Mean is also not a bad bet probably as of now. But let's say if they are outliers, then probably median is a safer bet. So that's why let's say we are going with median over here to fill in the missing values. First of all, we save the median value from the previous year rating column, and then we fill it in the column over here, and we are making the changes onto the data frame. That's why we are saying in place is equal to true. All right, so let's run that. And what we are going to get is our data set would now be filled over here, right? So in that case, we are not going to have few values over here. So Sandeep has a good question. What if this is the first year for the employees in the company, right? So that is a fair enough bet, but I would still argue if there's a new recruiter, new person who has joined, we can probably say that the new person is likely to perform at a median level, right? So the doubt is a fair enough doubt that Sandeep has, that what if that this is the first year that the person has joined in, and this is the first test that they're going to give. So we are assuming that they are performing at a median level, right? They are not going to be exceptional. They're not going to be low in the ratings. They are going to perform at a median level. All right, so let's move ahead. Now we have a lot of text columns into our data set that you guys mentioned: department, region, education, gender, and recruitment channel. And this time for convenience, we are using the simple ordinal encoder to code these values onto numbers. And we write a small for loop to do it more efficiently. We can do it one by one using each column as well, but let's be a little more efficient by using a for loop. We have put all these columns in a list, instantiated our ordinal encoder, and we are going to transform all the values to numbers. Okay, so once we do that, let's have a look at our data set now. So very conveniently for us, all the values are now in numerical. So we have department, region, education, gender, and so on. Everything is now encoded onto numbers. Let's just cross check whether there are no null values again. And I'm using df.isNull.sum.sum. How this work is that if we just have df.isNull, we are going to get for each and every value, is it a null value or not? We are going to get true if it's a missing value. So if we sum all the trues which are taking one values, then we can mention our sum over here. And finally, if we do a sum, what we are going to do is we are going to get the sum for each column. Is each column having missing values? But if we want to know it for the entire data frame, we are again adding one more sum so that we see, okay, the entire data frame has 0 missing values. All right, so let's move further. The next thing that we should always look for in when we talk about classification problems is class imbalance. Is there class imbalance in the data set? So before I go on and talk about it, can you guys quickly tell me, are you aware of class imbalance? And our data can be misrepresented. There could be different weights, and our models may not learn the kind of things that we want the model to learn. And count plot is a very good plot to look for class imbalance. So what we are doing is we are looking at our target variable and we are plotting how many values belong to each class. So we see the zero class, which is the not promoted class, is present approximately 40,000 times. And I think our data set was around 43,000 or so. So that means we can say around 3,000 values are there which are getting promoted. So there's a huge class imbalance over here. That means our model by default is going to learn more about the zero class and less about the class one. And this is actually the more important class for us. We want to predict who is going to get promoted. So this is a bit of a problem. But it's good that we have taken note of this and we will try to rectify it as we go ahead. So there are two, three ways that you know that you might be aware of in which we can do this. One is the class weight algorithm, class weight, sorry, hyperparameter. So are you aware of the class weight hyperparameter? Maybe I can get some quick responses. Don't worry, we are going to learn about the class weight argument. The other way to go about it is resampling or maybe using some techniques like SMOT. Are you aware of those? SMOT is, and there are several other techniques which are available, and many of them are present in a library called I am balanced and or imbalanced, if you want to call it like that. But we are going to use a different approach. We are not going to use the imbalanced library, SK imbalanced library, or SMOT techniques. We are going to use a different approach this time to try to rectify for class weights. All right. So I think let's that's mostly about it. We are just going to now separate the data set. We are going to remove our employee ID column from the data set, and we are going to add promoted. Okay, but before we go ahead further, but since we observe that there's a huge class imbalance, we can't use accuracy anymore. So accuracy is out of the different parameters that we listed for classification. We can't trust accuracy anymore, and we are going to use F1 score. So is everyone clear why accuracy cannot be used? If somebody is not clear, please mention it on the questions panel. And maybe if you can explain it to me as well, that would be great on why can't we use accuracy if there's class imbalance. And F1 makes it very nicely. So it's rare that recall and precision are used in industrial scenario as metrics of choice. So Komal points out that because of imbalance, accuracy cannot be trusted. Sandeep says if we predict that all are not promoted, if we say that all the 43,000 samples are not promoted, still we are going to get around 90% accuracy because we would be right 40,000 times. If we say all 43,000 samples belong to class 0, we would still be right 40,000 times and we would still get decent enough accuracy. That means accuracy cannot be trusted as a good parameter for this analysis. And let's say we decide to go for F1 score, one of the most popular metrics out there to compare classification algorithms. All right, so next what we are going to do is we are going to separate our features. We are going to remove our target variable. We are going to drop the target column is promoted. And as you mentioned earlier that employee ID is not required, so we are going to remove that as well. And onto why we are saving the target variable. Next, we split the data set by using train test split, and we are using some parameters over here. All right, so stratify is equal to y is another trick that you should always use whenever there is class imbalance. It is always a recommended thing for class imbalance. What it does is, and as Shiva points it out, what it does is it makes sure that there's a similar representation of both the classes in the training and the test set. So for example, let's say if we have our training set, and in the training set, let's say the ratio of 0 and 1 classes is, let's say, 80 to 20. A similar kind of ratio is followed in the testing set as well, that there is a 80-20 bias or 80-20 ratio between the two classes. Otherwise, what might happen is that by chance you may have that in the training set you have an even more highly skewed ratio, that you have, let's say, 95 over here, 5 over here, and while we come to the test part, maybe it would be, let's say, uh, 60 and 40. And that's not going to be very good for our model training process, because we are training our model with almost very few samples which belong to class 1. So stratify is equal to y, make sure that a similar kind of bias between the two classes is there in the training and test. And it's not going to be exactly same, but it's going to be very similar, maybe up till 1 or 2 digits. That's what it means, right? That means it's looking at a target variable y, and it's making sure that the 0 and 1 classes are being distributed evenly. Okay, so that's the reason why we do it. And you don't need to use it in case you don't have imbalance. So in case all the samples are equal like this, then you don't need to use stratify is equal to y. It is something that you should use particularly in cases where you face class imbalance. All right, so moving on, let's divide our data set and let's look at the first few rows of our data set. So now it looks like everything is ready. We have our training set ready over here. And as some of you mentioned, that probably scaling could be a good thing to be done over here. So that's what we are going to do next. We are going to import standard scaler, and we are going to sort of fit the model on train and only transform the test set. Remember that when we talk about the testing set, it is the totally unseen data set. We don't want to learn any information from the testing step. When we talk about standard scaler calculates the value based on the mean of a column and the standard deviation of a column. We don't want to feed information about the unseen data set onto the mean and standard deviation. That's why, as a practice, you should only use the fit method on xtrain and only use transform on xtest. That means we are transforming xtest based on the mean and standard deviation that we learned from the training set. In a way, we are leaving the xtest totally untouched, as it should be. We should not do too much interference with the testing set. We should not look at the data set too much. When it comes to the testing set, we should let it be unseen data set. So that is the reason, as a practice, you should always fit transform on xtrain and only transform on xtest. I see a lot of people making the mistake of transforming the entire data set. And that is a problem which will not be detected while you're training the model, but once you actually put your model on the production stage, you would be surprised by slightly lower results. So that is something to be cautious of. But always make sure that you train on the training set and always just use transform on the test set. All right, let's move forward. And now what we are going to do is, now we are going to come to the algorithms part of things. So we are going to start with the very first algorithm that is on our table, that is logistic regression. So we are not going to discuss it in detail. We are going to talk about it very briefly. But if we talk about logistic regression algorithm, it is a binary classification algorithm. Originally, it was designed for two classes, and then there were some modifications like one versus rest, which can modify it to multi-classification problems as well. Now, logistic regression is very similar to linear regression. If we talk about multilinear regression, what we have is we make our prediction based on this equation, where m is the slope values and c is the intercept values, and x1, x2, x3 are features, right? So this is a kind of equation that we use for multilinear regression. Now, what works for regression does not really work for classification. When we talk about binary classification, our target variable lies between 0 and 1. Whereas this particular output can take any value from positive infinity to negative infinity. And therefore, we use a nice function called a sigmoid function, which has a wonderful capability that it can transform any value from negative infinity to positive infinity to lie between 0 and 1. So this is how a sigmoid function is given by, where E is Euler's constant. And what we are passing on to this is the entire output of the previous step. So we take are similar equation like linear regression, and we pass it on to a sigmoid function. And that gives us some predictions which lies between 0 and 1. And so maybe some prediction would be zero point 0.2, some prediction will be 0.8. And since our prediction lie between 0 and 1, we actually read them as probabilities. And we read them as probabilities of belonging to class 1. So if we have, let's say, x as maybe something like this value, maybe 2 or 3, let's say if the output of this equation is, let's say, 2 or 3, then we get a probability of 0.8 that this particular sample belongs to class 1 with a 80% probability. And you might have seen a logistic loss function up till this point. You might have seen that the loss function is represented till this point. But let me ask you, are you also aware of regularization in multilinear regression? Do you know about L1 and L2 penalties? So I'm not going to talk about regularized regression as of now, but maybe during the Q&A, I can give you a little bit of idea. And yes, by regularized regression, I do mean lasso and ridge, as some of you are pointing out. So yes, I'm talking about lasso and ridge regression. Now, this is what we mean by regularized regression when we talk about multilinear regression. Now, a bystander, the model in logistic regression that we have in scikit-learn, that is also regularized, right? And in fact, we can choose, are we going to use an L1 penalty or are we going to use an L2 penalty? And the penalty that is being used, L1 or L2, is sort of controlled by a parameter C, a capital C. So this is the C that we have in logistic regression that we try to control. So this is the standard loss function for logistic regression, where P is our predicted probabilities. So let's say in this case 0.8, right? So this function is something that we try to minimize using gradient descent. We try to minimize this function, try to find the right values of M1, M2, M3, and so on. And if it's a regularized logistic regression, then there's a added penalty. Essentially, what this particular function is doing is it's making sure that our slope values M1, M2, M3 are not too high. If they become too high, if we let them be unrestricted, there's a high chance of overfitting. So essentially, by adding the absolute values of these coefficients to our loss function, essentially, we are trying to control for overfitting, making sure that our weights or our coefficients don't take very, very high values. So if we talk about some key hyperparameters, and there are other parameters as well, like some of you mentioned solvers, but if we talk about the key hyperparameters, I would say C is one of the most important hyperparameter for logistic regression. If we increase the value of C, then we decrease regularization. That means there would be a higher chance of overfitting, and vice versa. So let's just quickly see it. Let's say if in this function, if we say that the value of C is 1000, now in this equation, it is 1 over C. That means this term will become very, very small, very, very tiny. And therefore, it will be almost being similar to 0. That means in a way, we are canceling out this term. If we are saying C is equal to 1000, and our loss function remains the standard logistic regression loss function. Whereas on the other hand, if C is very, very low, let's say if we make C as 0.01, then we are giving a very high weightage to this term because it is 1 over 0.01, which is going to give a high coefficient to this particular term out there. So C is one of the most important parameters over here. So Sheikh says, is this a lambda parameter? Yes, you can say that it is a lambda parameter. So in fact, when we talk about linear regression, it is mentioned as alpha. So right, when you talk about lasso and ridge regression, you tune something called as alpha. And when we talk about C, then you can say alpha is equal to 1 upon C. And some people like to call alpha as lambda. So that is also fine. So this is the relationship between alpha and lambda, right? And lambda and C. All right, so this is one aspect of logistic regression. We are not going to go into too much depth of logistic regression. Other important parameter that I would say it's there for logistic regression is class weight. And this is the one which can handle class imbalance. What it does is, if we pass an argument called balanced over here to class weight, what it's going to do is it's going to make sure that the class which is present less frequently, we give higher weightage to the loss term for those samples. We give a higher weightage to the loss term for those samples. That means our model will be forced to learn about the class which is not present that frequently. So the popular parameter is balance, but actually we can give a ratio to this argument as well. We can give a dictionary that give, let's say, the zero class an importance of 1 and give an importance of class for class 1 to maybe 4. So we can actually do that as well. But generally mentioning balanced is a safer bet. It takes care of making sure that it gives more attention to the class which is present less frequently. So let's go to our model and apply logistic regression onto our promotion data set. So let's go over there. What I'm going to do is I'm going to import logistic regression, and simultaneously we are also importing F1 score, and I'm also importing a library called time, which will help us keep track of how long does it take to run a particular algorithm. So let me import these few things. The next part is pretty usual that you would be familiar with. We are instantiating the algorithm, fitting it on the training set. So it says that total number of iterations reach the limit, but as of now, we are not increasing the iterations. We are letting it to be how they are as of now. And you see that we see some hyperparameters that we are talking about. Class weight is there, and we have the C. So by default, the value of C is 1. We would want to tune the value of C only in case there is overfitting. If there is no overfitting, then it's fine. We don't need to really tune for C. C helps us in controlling the overfitting. If there is overfitting, we would like to decrease the value of C. All right. So, and you see there's an option of penalty over here. By default, there's an L2 penalty that we are applying, which is the same thing as applying ridge penalty. And we can also choose this penalty term for L1 if we want to apply lasso penalty. All right, so after we have fit our model, what we are going to do is we are going to make predictions of F1 on the training as well as on the testing set. So let's see what is our F1 score on the training and testing set. So the good thing is that there is no overfitting. Our training and testing F1 scores are all quite similar. The bad thing is the F1 score is quite low. The closer the F1 score is to 1, the better it is. And this one is not impressive at all, right? 0.16, 0.17. This is not something which is satisfactory. So now we are going to use a simple trick. We know that our data is imbalanced. So we are going to use the hyperparameter class weight, and we are going to say, let it be balanced. This time we are also recording for time, and we have also put up a timer at the end of the code. And we are just going to subtract the 2 time units to tell us how much or how long does it take to run this piece of code. Rest of the things are similar. We fit on the training set and check out the F1 score after we make predictions on the training as well as on the testing set. And we are looking at the rounded numbers. So I'm using np.round over here so that we can get values up till 2 decimal points. All right, so once we run that, we see that just with this particular hyperparameter, our F1 score has improved significantly. Our testing and training scores are again in a very similar range, and the values that we are seeing is around 0.32. Also, our code executed in a fairly fast manner. The code got executed only at 0.41 seconds. So this was quite a fast implementation in terms of running our code. So these two things are appearing to be fine. So there's a decent improvement by just mentioning this hyperparameter class weight as balanced. All right, now let's understand how is it that a logistic regression is making the key decisions. And to understand that, we are going to use the function that we were talking about earlier, we are going to use the plot decision regions functions that we were talking about earlier. What we are going to pass on to this is our features, our target values, and we choose two important features. We are choosing the feature which is at the index 8, and we are choosing a feature which is at the index 11. So this can only be done for two features, and we are fitting our algorithm logistic regression, which we have defined earlier. We are going to fit this particular logistic regression algorithm onto our data set. So let's see what this particular code does. All right, so there is a lot of information in the graph that we have got over here. Let's try to understand this information one by one. Now, what this function does is, this function takes all the samples and plots them. And we are looking at two features, average training score and length of service. So based on only these two features, the classifier fit the algorithm. And we see all the samples being plotted over here. So the triangles are labels which belong to class 1. So the blue triangles are for class 1 and the red ones are for class 0. Finally, if we talk about the sky blue region, or whatever this color is, blue region or sky blue or teal, this region corresponds to the locations in our average training and length of service combination, which will be predicted as 0. So if there's a point over here, our model is going to predict it as belonging to class 0. Vice versa, any combination of average training score and length of service which lands in the gray area will be predicted as label 1. And observe over here, this is how logistic regression is making a decision. Logistic regression is dividing the two regions with a straight line. So this is what we mean when we say that logistic regression is a linear model which makes a straight line differencing between the two classes. Any points which are over here at the top region will be predicted by the model as belonging to class 1. Any combinations of the two hyperparameters which are over here will be predicted at class 0. So for example, let me just change the color of the pen to explain it to you. For example, let's say if we are looking at this particular point over here. So this is a sample, there's an employee who has spent 25 years at this company and has an average training score of 50. The logistic regression is going to make a prediction that this belongs to class 0, not going to get promoted. Whereas if we talk about any samples which are above, let's say, what is this value, 65 or 66, any samples which have an average training score above this values, our logistic regression is going to make a prediction that it is going to belong to class 1. That means all these red points are errors, which red points we saw are belonging to class 0. They are in the gray zone. So all these red points over here are errors. Similarly, if you talk about the lower zone, all the blue point are errors because this zone is supposed to be for 0 class. So all the dark blue triangles, they are error points, the points which are being wrongly classified by our models. So the key thing which this graph is telling us is how is it that the logistic regression model decided to take a decision. It decided what is going to which class by making a straight line. It found a straight line which according to it classified the algorithm in its best capacity, and that's how it decided to train the model. Now if we were to add more features, this would not be a line, but you can think of this as a plane. But we have challenges that we cannot visualize something which is more than 2 dimensions. So this algorithm right now, logistic regression, is fitting based on only two features, average training score and length of service, which actually happen to be one of the most important features, some of the most important features in this data set. But the key thing is that the decision boundary is quite simple. It's just a linear straight line. That is how logistic regression is making a call. All right. So let's go ahead to our next model. So the next model that we are going to go for is the SVM model, or support vector machine model. So before we go to SVM, let's do a quick recap of what is it that an SVM model is. Now, SVM model is a large margin classifier. If we talk about the linear version of support vector machine model, the main goal is that it's very similar to the logistic regression, and the main differencing part is that what it does is that it tries to maximize the distance between the two classes that it is encountering, right? What it does is it tries to maximize the two classes that it is encountering. Now, the goal is for SVM to maximize this distance, and it does it based on the parameters which are on the boundary. So these points, and there's a name for these points. These points which are on the edges of the boundaries are called as support vectors, and hence the name support vector machine model. Now, this is a standard part of support vectors, which is not that interesting. The interesting part of support vector comes with the use of kernels. Now, logistic regression, as we saw, fits a linear decision boundary, a straight line decision boundary between the data sets. And as we saw in this particular data set, it was not looking to be a great decision boundary. We saw there were a lot of errors on either side of our decision boundary. And probably we need a more complex decision boundary which can fit non-linear curves. Now, kernels in SVM helps SVM fit non-linear decision boundaries. How does it do that? What it does is, let's say if these are two features, feature 1 and feature 2, and let's say that these red triangles represent one particular class and these blue dots represent another class. Now, right now, if we try to fit a linear boundary, you can try it later on, but there is no way in which we can perfectly divide the two classes. Maybe let's say if we decide that, okay, here is the decision boundary, it's not perfect. There are some errors on either sides. Maybe we try this as a decision boundary. Again, these points are errors. So there's no way in which we can actually fit a straight line on this data set which can divide the two classes perfectly. But if you notice over here, both the feature 1 and feature 2 values are lying between 0 and 1 values. 0 and, sorry, or rather 1 and -1. Right? So they are all lying between somewhere over there. And that means all the red triangles are over there, whereas the blue triangles are taking higher values. So if we do a simple transformation like squaring these values, if we square all the features, features 1 and feature 2, what would happen is that the blue samples will take a higher value because square of negative or positive numbers which have high absolute values are going to sort of be giving higher values. And whereas when we talk about triangles, they sort of come and show lower values because they were close to 0, and when we square them they become even smaller values, and now it becomes possible to fit a linear boundary. So in effect, this is a quick representation of how kernels fit non-linear boundaries by transforming our dataset. How extensive is our transformation? What is the level of transformation that we are doing is determined by a hyperparameter called gamma, right? Now, when we talk about gamma, if we take a high value of gamma like over here 2, then our decision boundaries are become very specific, right? We are taking one sort of value over here, and then we are saying any points which come in this blue region we are going to label as belonging to one particular class, and any samples in this red region we are going to say belonging to one particular class. Whereas if we reduce the gamma value, we get a more general kind of boundary like this, that all the samples in the blue region we are going to predict belonging to blue class, all the samples which exist over here red class, and this is somewhere in the middle, gamma 1 and let's say feature 1 over here. So let me ask you a question. Depending on what we have seen over here, if let's say if our data set with SVM is doing a lot of overfitting, should we decrease the gamma or should we increase the gamma? What should we do in SVM? If our model is currently overfitting, we should decrease the gamma, because if we decrease the gamma, we are going to create a simpler decision boundary, which is going to be more general. It is going to help us create a better model. So gamma happens to be one of a key hyperparameter when we talk about SVM. Apart from gamma, we also have C over here. Now C, although the effect of C is very similar to logistic regression, that if we decrease the value of C, we are going to get more regularized model. The calculation is slightly different, so it is not exactly as logistic regression. So this is not how C is represented in SVM. It is represented slightly differently, but in terms of the effect, it is very similar to logistic regression. We also have as our argument of class weight, just like logistic regression. And finally, one of the key parameters is kernels. And the most popular kernel out there is RBF, or radial basis functions, although there are other kernels like sigmoid, like polynomial as well, and of course linear as well. But RBF tends to be one of the more popular ones. So on that note, let's go to our model, and now this time let's try out SVM. Now SVM is going to take a little bit of time, so I would be probably taking that time to answer a few questions. So first of all, we are going to import SVM, and then what we are going to do is we are going to run the model. But I'm going to do slightly, I'm going to cheat a little bit over here in the interest of time. What I'm doing is I'm fitting, let's say, RBF kernel, and we are mentioning the class weight as balanced because we already know this is the imbalanced data set. But in the interest of time, I'm only fitting in 20,000 rows. I'm not fitting in the entire rows of xtrain, but you can take my word for it that the F1 score will not change much even if you increase the data set. But later on you can try. Right now, in the interest of time, I'm just using 20,000 rows. Still, it's going to take quite some time. But we can imagine if we have the entire data set, it's almost going to take double that time. So after we fit our model, we are also making predictions of F1 score for both the training and the test set. And finally, we are also going to print how much time is it going to take. All right, so meanwhile, our model has fit, and you can see that it took decent amount of time, 53 seconds. So in terms of computational speed, SVM, particularly with kernels, is probably not the desired model. 53 seconds, and score is also not something to talk about much. So it's around 2.27, 0.28, not something which is very, very impressive. One interesting thing is that you can actually look for the support vectors which are there for each of the classes. So it says that there are these many support for the zero class, and there are these many supports for these class. And in fact, you can actually get the coordinates of the support vectors as well with an attribute in SVC if you are interested. Yeah, so this particular attribute will give you the coordinates of the different support vectors as well in case you are interested. Right now, let me go back to the n support, the number of support vectors out there. All right, now let's talk about decision boundary. Again, you see I'm going to use an even bigger shortcut over here because if you try it with the entire data set, it's going to take a lot of time. So I'm going to first run it, and I'm only making a decision boundary with 2000 samples, again in the interest of time. We are using the same features number 8 and 11, which is our length of service and average training score. We also have our kernel RBF, and we have our class weight as balanced, and we have a gamma of 0.1. All right, so this is the kind of decision boundary that we get. First thing that we immediately notice is that this time it's a non-linear boundary. It is not a boundary like we were seeing in the early example with logistic regression. This time the boundary is non-linear. We have these kind of pools over there which are predicting regions for different classes. Again, gray being for class 1, and we can point out over here that we see that there are a lot of blues over here, and then we see certain pockets of blues over here as well, and all the region which is in sky blue color that is being used to predict the red class. But the interesting thing is that our model is able to give us these specific designed labels this time. It's not a simple decision boundary. Our decision boundary has become complex right now. Let's play a little bit with gamma and see how is it our decision boundary is going to change. In fact, let me ask you first and then I'm going to run it. So it's going to take some time, and we see that SVM is a little bit of a slow algorithm. We see that particularly with the plot decision regions function, it is acting out little slow. And that is one of the key drawbacks of SVM actually, that it can take a lot of time to fit, particularly when we are using kernels. And you guys were right that it is indeed going to create a more complex boundary if we are creating gamma as a higher value. And therefore, if we want to create a more general model, we would want to decrease the value of gamma. We see even for 1 point, it is creating a decision boundary over here, just 1 point. And it has said that any points which occur in this range, this entire range, we are going to label it as belonging to class 1. So this is a classic example of how we can identify overfitting. This is clearly overfitting happening. Just based on 1 point, it's making a region that any point which occurs in this region, we are going to make a prediction that that belongs to class 1. So SVM adds complexity to the model, also adds the risk of overfitting with these complex boundaries over here as well. All right, so on that note, let us move to our next algorithm, which is going to be KNN. So let me go over there. KNN algorithm. Now, a KNN algorithm is one of the simpler algorithms out there. And what it does is it basically sort of tells us based on the distance and the number of neighbors, we take a majority poll on which particular class a sample belongs to. So for example, let's say if this is a particular sample for which we want to find a label, and we have two classes, one is class A in yellow, the other is class B in purple. And let's say if you're looking at the three closest neighbors, then we see, okay, how many samples belong to class A and how many samples belong to class B. And we see over here that if we look at the three closest samples, two samples belong to class B and only one belongs to class A. So we are going to say that this particular sample belongs to class B or the purple class. Similarly, if we go for six closest neighbors, if we look at these neighbors, can you tell me what is the class that we are going to predict? Is it going to be class A or B? And as many of you have quickly pointed out, we are going to go with class A because in that case, four samples are going to make a prediction of class A, whereas only two samples say that we are going to predict class purple. Now, KNN algorithm is actually quite different compared to our other algorithms. The reason being is a KNN algorithm does not try to store the generalization of the model. What it does is it saves all the data points onto the memory. So all these data points are saved onto the memory. And as and when a new sample is there, which we want to make prediction on, let's say if there's a new sample which is there, then it just looks at the entire data set, checks out for the desired number of neighbors, and checks which of them follow which particular class. And based on that, we make predictions. And this, because of this fact, because it actually saves all the parameters, this is a very slow model as well. Maybe not as slow as SVM with kernels, but still it happens to be quite a slow model. If we talk about hyperparameters, the key hyperparameter when we talk about k nearest neighbor is the number of neighbors that we are going to look at. So let me ask you, what do you think? If we increase the number of neighbors, are we going to get prone to overfitting or are we going to get prone to underfitting? If we increase the number of neighbors, that means if you're looking at more number of neighbors to decide whether a sample belongs to a particular class or not. It's actually the underfitting part. Or in a way, you can say that we are going to get away from overfitting. The reason being is that what we are doing is that we are looking at multiple models out here. So in a way, when we are saying that we are looking at large number of neighbors, we are taking a bigger poll. Think of it as elections. If we do elections, let's say in India, and we decide to only ask three people on who should be the prime minister, that would be a very, very biased view. But if we decide to go for all the 1 billion people, then probably we are going to ask a lot of people, right? But then it also means that maybe we'll miss out some of the close relationships, that who is closest is probably most accurate. So maybe people who are very sort of highly inclined towards policy and economics and decision making, maybe they can take a better decision on who the prime minister could be. But again, so we are talking about proning. We are not saying it's actually going to happen. So generally, when we say that if we increase the value of k, we are going to increase the regularization, or we are going to decrease the chances of overfitting. Now, k happens to be the most important hyperparameter, but there are some other hyperparameters. One is distance, that if we don't give equal weights to all the points, if we say that the points which are closer are going to have higher weights in voting, that is also something we can use. Finally, how do we calculate distance from of one point from the other? That is also a hyperparameter. I would say not a very important hyperparameter. The standard is the straight line distance, which is actually Minkowski with something as p equal to 2. I'm not going to get into the details of the metrics as it's not a very important parameter, but there are some other measures also through which we can calculate distance between the points, and we can choose those other metrics as well. The most important parameter is the number of neighbors. So what I'm going to do now is I'm going to go ahead and fit the KNN model out there. So let's shift to our Jupyter notebook. We are going to import KNN, and we are going to now fit KNN, and I'm randomly going with 8 number of neighbors. We can play it with it later on. And then let's say we are fitting the model. We are also monitoring for time, just like we have been doing so far. And so it is slow, but not as slow as SVM. This took 6 seconds. It took more time than logistic regression, but was still fairly fast. Accuracy may be slightly overfitting. Not too much, but maybe a little bit of overfitting is happening. So maybe we could later on try to increase the number of neighbors. Let's look at the kind of decision boundary that KNN is making onto our data set. It's going to take a little bit of time. So actually let it run. I think it's going to take around maybe 10-15 more seconds. Otherwise, in the interest of time, let's do one thing. Let's move to our next model, naive based. Let's discuss that. Actually, let's go to the next model, which is the naive based model. Now, naive based model is very different compared to the last two models that we have talked about, SVM and KNN. It is different because it is an extremely fast model, one of the fastest models out there. It gives us result in a very fast manner. If we quickly revise what is a naive based model, it is called naive because it makes a very naive or simplistic assumption that each feature is completely independent of the other feature, that there's absolutely no relationship between any of the features out there. Why is it called Bayes? Because it is based on the famous conditional probability theorem, which is called as Bayes theorem. And if we talk about Bayes theorem, it is given like this, that the conditional probability of A occurring given that B has already occurred is given by the opposite of that, the probability of B occurring that given that A has already occurred, multiplied by the probability of A, and this is entirely divided by probability of B. So what naive Bayes essentially does is it calculates these probabilities for these different scenarios. To give you an example, let's say if in our case, there's a particular sample or a particular employee who has an age of 50 and a gender of male, what our naive Bayes algorithm would do is it will explore our data set and find all these probabilities. It would find out what is the probability of the age being 50 given that it is a yes. Similarly, what is the probability of gender being male given that it's a yes? We would multiply it with the total probability of a promotion, which is what we are denoting with yes over here. And finally, we are going to divide it with the probability of age being 50 and the gender being male. And these kind of probabilities are calculated in a very fast manner in naive Bayes model. Another fascinating part or good part about naive Bayes is that we don't need to tune any hyperparameters. There is something called as sort of smoothing, but that is not a very important hyperparameter. That is sort of more for protection, in a way that because we have a lot of divisions over here, just to sort of kind of protect our probability is that there's no division by zero kind of thing. But otherwise, there are no hyperparameters, so to speak of, in naive Bayes. And that's a good part about naive Bayes. So let's go over to our Jupyter notebook. Hopefully our KNN would be ready. And it is indeed ready over here. And what we notice is that KNN also fits in a non-linear kind of boundary. Again, a complex boundary which is slightly non-linear. Now I'm not going to run it with a different number of neighbor because essentially it's going to take a lot of time. Right now it took 56 seconds, but this is something that you can play with later on. Try to change the number of neighbors over here and see how the decision boundary is changing as you are changing the number of neighbors. Intuitively, if you reduce the number of neighbors, the boundary is going to get more complex, prone to overfitting. And as you increase the number of neighbors, the boundary is going to keep on getting more simpler, getting more general. Okay, so this was all about KNN. If, as far as F1 score is concerned, so far still our leader is logistic regression. Whether it is SVM or KNN, none of them have been able to give us an F1 score of around 0.3. All right, let's talk about naive Bayes model, and we are going to use Gaussian naive Bayes model, which further makes the assumption that our features are distributed in a Gaussian manner, or in other words, in a normally distributed manner. So we are going to import the model and let's see how it fits like a charm in a fraction of a second. So even before we ran it, the model was showing the results. It took just 0.08 seconds to run naive Bayes model. And that is one of the key perks of naive Bayes models. And the performance is actually not that bad considering the time it took. It is quite close to the performance of the KNN model. All right, so let's look at the decision boundary. Now I'm going to do a slight trick over here. I'm not going to use the same features 8 and 11, but I'm using different features. I'm using 10 and 11. The reason is that if I just use 8 and 11, it's not going to show the other class at all. So if we do 10 and 11, if we take the average training score and awards 1, what it is essentially saying is that whatever samples belong to the class where they have not won any awards, make a prediction that they are going to belong to class 0, not going to get promoted. And essentially it is saying that everyone who has won an award, make a prediction that they are going to be of class 1, that we are going to make a prediction that it is going to belong to class 1. The decision boundary is also not very complex. Just to show it to you, in case we decide to use the same feature that we have been using so far, we are only going to see one class out there. We are not going to see the other class. In a way, our model is saying that just predict everything is 0. Just make a prediction that nobody is going to get promoted, right? So that's why I was not showing it to you with feature 8, and I was instead showing it to you with feature 10. All right, so on that note, let's move to our next model, which is going to be our decision tree. Now, decision tree is another fascinating model, and one thing that is there in decision tree is there are a lot of hyperparameters. So there are a lot of things that we need to tune when we talk about decision trees. So how the model works is, in decision tree, we keep on dividing our data set till it becomes a pure class. So you'd keep on dividing our data set into different branches till we get pure classes at the very end. And the goal of the decision tree is to minimize impurity. What do we mean by impurity? If let's say there are mixture of samples, so let's say if there are 30 samples which belong to 0 class and 20 samples which belong to class 1, there's mixing over here. There are items of both the classes which will lead to high impurity. The objective of decision tree is to reduce the impurity so that maybe let's say over here all the items belong to class 0 and maybe over here all the items belong to class 1. The objective of the decision tree is to split the dataset as much so that it creates pure leaf nodes which only have one kind of class. Impurity can be defined in either of the two ways. Either we can use an entropy measure or a Gini measure. In practical scenarios, it does not make a lot of difference whether we use entropy or Gini. As you can also observe from the formula, they are a little bit similar, where each with the value P is signifying the probability of a particular class occurring. So in this case, if we talk about class 1, the probability of class 1 occurring is 20 by 50. That would be the P of class 1, that would be 20 by 50. And similarly, if we talk about P of class 0, that would be 30 by 50. So for each node, we calculate these probabilities for the two different classes, and then we can use entropy or Gini formula to actually check out what is the impurity values. And the idea of decision tree is to split the dataset in a manner that the impurity becomes zero. So at this level, there is no impurity, there's only one class, neither is it at this level. But this craziness of getting to the lowest impurity possible is a two-edged sword, because there's a high chance that our model is going to overfit. By splitting the dataset as much as possible, there's a high chance of overfitting. And one particular hyperparameter which can help us in controlling how much are we splitting is max depth. So let's say we decide that if you only want to have a max depth of 2, that means don't split after a couple of points. Don't make these splits. Let these be our final predictions. And this helps in regularization. So if we have a lower max depth, again, let me ask you a question. Are we getting prone to overfitting or underfitting? Think about it for a few seconds and let me know if we have a lower max depth. So low max depth, maybe let's say of 2. Are we prone to underfitting or overfitting? So as some of you are pointing it out, it's actually going to, and in fact, this time it's a clear majority. Almost everyone is saying it's going to be underfitting. And as a contrast, if the max depth value is high, we are going to overfit. By default in the model, the maximum depth is not restricted. That means by default, the algorithm says split the dataset as much as possible. Keep on splitting it as much as possible. We also have our class weight in this particular algorithm. And do note that we don't have class weight algorithm in naive Bayes and KNN, right? So those two algorithms don't have the hyperparameter of class weight. We cannot have a class weight algorithm in those class weight hyperparameter in those two algorithms. Finally, there are other ways in which we can also prune our tree or cut our tree or restrict our tree, and they are sort of they have sort of similar effect as max depth, and one of them is minimum sample split. In a way, we are saying that this particular node should have a minimum of 50 samples before we decide to split it further. If there are less than 50 samples in this branch node, don't split it. Very similar hyperparameter is minimum sample leaf. It says that once our data is split, there should be, let's say, minimum 10 samples in each leaf. You should not create leaf nodes which have just 1 or 2 samples. Now, these are some of the important hyperparameters, but there are a lot of other hyperparameters which are not as important, like choosing which impurity do we use, Gini or entropy. Max features is not important for decision trees, but it is going to be important for random forest. Similarly, minimum impurity decrease, minimum impurity split have a very similar kind of effect as minimum sample leaf and minimum sample split. So that's why I have put them in not so important categories. And similarly, random state as well, I'm putting in a not so important categories. Random state again helps us in getting similar results after we run the model multiple times. All right, so that's about decision tree. We are also going to plot a decision tree onto our Jupyter notebook. So first, let's actually plot the tree, and then we are going to actually run it. So there's a nice tool with sklearn called plot tree. And first of all, we are going to plot the tree. I'm going to use max depth of 2 so that we have decent amount of space over here. We are creating a decision tree with a 2 max depth. We are fitting it onto our model of with complete data set, and then we are showing what is it that the decision tree will do. We see that which feature are we splitting on. We are splitting at feature 11, and what is the decision criteria for splitting? We are saying if the value is less than equal to 90.5, that is the splitting criteria. Initially, the Gini value is 0.156. That means if we split the data set, the Gini should go down, the weighted Gini value. And we also see the number of samples that we have for each of the classes. Once we split the data set, we see that the Gini of this particular node is 0.142 and the Gini of this is 0.217. Now you might be wondering that the Gini value has actually increased over here, but we don't look at node specific, we are going to take a weighted average. And since most of the samples are in this node, so if you take a weighted average of 43,000 times 0.142 plus 468 times 0.217, it's still going to be lesser than 0.156. So this is how a Gini or a decision tree is structured. Let me just skip this part because many of you have already seen this kind of diagram. Let's come to the meaty part of the business. Let's train the model and let's fit it. So here we see a bit of a problem. We see that decision tree is overfitting a little bit. Although it is a two-edged sword, the test score that we are seeing is one of the highest scores that we have seen so far, 0.36. But we also see a little bit of overfitting because there is a max depth that which is significantly higher. In fact, let me show even more overfitting. If we don't mention a max depth and if we run a model, we see what is the peril of decision tree. It is giving us 100% sort of a F1 score on the training set, but only a 0.4 score on the testing set. So this is one drawback of decision tree, that it can overfit quite a lot. In terms of time taken, it is satisfactory. It is not taking too long time to fit. But the main problem is that decision trees are highly prone to overfit. And therefore, max depth really helps us in making the algorithms sort of fit better. If we make a max depth of 11, we see that our testing and training score are now a little bit closer compared to how they were if we were restricting the maximum depth. Let's understand this with decision boundary as well. Now, if we look at decision boundaries of decision trees, they are in shape of boxes. We take these square decisions, and in a way, like the chart that we were drawing over here, it comes out with values. If x9 is less than or equal to 0.5, then split it. That means these are the kind of decisions which are being taken in a line over here. And again, you see that there are some tiny gray boxes over here, which is again a classic sign of overfitting, that this kind of model can overfit because it's making very tiny regions where a particular class would be predicted. If we try to make it even worse, let's say if we try it without mentioning the maximum depth, and then if we look at the decision boundary, you see even smaller specific regions are built. And that is the reason why there's overfitting which is happening when we talk about decision trees. Finally, let's talk about our last model, but not the least, which is random forest model. A random forest model is a simple model which combines several decision trees together, and we have very different kind of decision trees, and eventually we decide to take a majority vote. For each sample, we ask the number of different decision trees on what should be the prediction, and we take a majority vote. And using random forest helps us reducing the effect of overfitting. It does not eliminate it, but because we are asking multiple trees, the problem of overfitting in decision tree reduces, but it is not getting completely eliminated. One of the key parameters in random forest is n estimators, which is the number of decision trees we should build. So let me ask you, if we increase the number of trees, are we getting prone to overfitting or underfitting? Is it O or U with high number of trees?
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions, and I will respond to your comments.